Okay, so now that we've been estimating the area beneath the curve, which is what we do in this class, when you go into a traditional calculus class for the STEM track, Analytical Calc 1, you go way deeper into this. We're just estimating the area in it, but why do we care about this? So how can we get our estimation of the area more accurate? And the answer is if we have more rectangles, we have less error. And you can see that in the picture right here that they've drawn. The first one has several rectangles, but not too many, and you can most certainly see some areas where it's underestimating when you're using those rectangles. So it seems like this is a close estimation, but it definitely does have some error. You look at the second picture, and it seems that they've almost doubled the number of, if not more, the number of rectangles. And when you add more rectangles, what you do is you have smaller error. So remember, n represented the number of rectangles. What do we want to happen if we want this to be more and more accurate? Is we want the number of rectangles, which is n, to increase. So how many rectangles do you want? Well, as many as you could. So what would that be to us? If you remember, if n's the number of rectangles, what we're really looking for is what if we had an infinite number of rectangles? We can't plug in infinity, but we certainly can do limits. So when you see the limit is n goes to infinity, that means we're using more and more rectangles. So this brings us back to the limits that we've seen from the beginning of the semester. Okay? It says let n be the number of rectangles and the width be delta x, which is the right endpoint minus the left endpoint divided by the number of rectangles. So it says right here the area of the ith rectangle is, well, what do? Well, you find the height by plugging that value into the function, and the width is fixed for you. Okay, and then what do you do with that? You sum them all. If you remember the summation notation here, the sigma means sum. So you're going to sum it for all n of your rectangles. If you have n rectangles, you add it up. So this right here represents the height. This right here represents the width. And this just says add all the heights and widths. Add all the areas of the rectangles. Okay? So this right here is how we've been estimating. This thing right here is how we've been estimating the area beneath the curve. So if we want this to be more and more accurate, what we wanted was more and more rectangles, and that leads us to this exact area right here. Beautiful formula. How do you find the exact area beneath the curve? You do the limit as n goes to infinity. In other words, you have an infinite amount of rectangles, and then you have the sum of f of x sub I delta x. So all that's saying is the height times the width, the area of the rectangles. We have n of them. And so you find the area of each one of those n rectangles and you add it up. Then take the limit as n goes to infinity, and that will give you the exact area. Well, as we talked about earlier, how do we already know exact area? We already knew exact area as a definite integral. So if we had the integral from a to b of f of x dx, that was the area beneath the curve of f of x on the interval a to b. So that has to be equal to our new thing right here, which is the limit as n goes to infinity of the sum of I equals 1 to n of f of x sub I delta x. So this is what this theorem right here, the definition of a definite integral, is what ties the idea of what we've been doing this entire section to what we've been doing in the previous sections. You can use rectangles to find the exact area. And if you're moving on to Calc 2, which most of you aren't because you're in brief calculus, a business calculus course, but if you're moving on to Calc 2, this idea of adding up a bunch of small pieces is a really, really big and really important topic. It's not so big in this class. This is all you're going to see about it. All we're going to do is estimate it with a few rectangles, and all we're going to do is use the definite integral. We're never actually going to go in and evaluate limits. In a traditional calculus class, you would find the sum first, and then you would evaluate the limits. But in this class, we don't need to worry about it. We're just going to stick to our estimations.